So today we're talking about hybrid orbitals, and with hybrid orbitals what we're trying to do is we're trying to make a connection between the theory that we have, quantum theory, explaining the behavior and the structure of the atom, and bonding, which for us turns out to be in the VSEPR shapes. So what we're going to do is we're going to start with our VSEPR theory. VSEPR theory, as we know, says that electron pairs, whether they're in bonds or as lone pairs, those electron pairs are going to be as far away from each other as possible, electrons repelling electrons. Quantum theory says that electrons exist in orbitals, or regions of probable distribution, and that they have wave-like particles, and key part of that, of course, is that they do not have a fixed location, which means they can be anywhere they want. And that's going to be kind of handy. Let's start with atomic orbitals, the orbitals that the electrons exist in the atom. We can have s-type orbitals, and then we can have p-type orbitals. And p-type orbitals can exist in three different orientations: up, down, left, right, in, out. When we put them all together in an atom, we end up with this big jumble. But what I want you to realize right now is that those p orbitals are right now at 90 degrees away from each other, which would make it a bit of a challenge forming bonds that have, say, for example, shapes like we see in VSEPR. So, for example, this molecule here, which has a linear shape, we could not do that with atomic orbitals. Now, you say, wait a second, I've got a left-right p orbital. I could bond on either end of that. Maybe, but don't forget, if I have a left-right p orbital, that's one orbital. So if I had a molecule forming by bonding something on both ends, I would actually end up with 4 electrons being shared in that p orbital, which I can't do. I can share a maximum of 2. If I were to look at this and say, okay, well, maybe I've got 2 separate p orbitals, that works. I can form bonds that way, but I can't do it at 180 degrees. I would have to have 90-degree bond angles. So atomic orbitals, while they're a really, really good starting point, cannot explain bonding, at least not VSEPR shapes, as we know bonding to happen. So what do we do? Well, how do we change the theory? How do we modify the theory? How do we add to the theory to accommodate VSEPR shapes? And what we use is something called hybrid orbitals. And a hybrid orbital is where we take 2 existing orbitals of different types and we somehow mix them together, mix them in their characteristics, mix them in their properties, and come up with a new kind of orbital that has slightly different properties, but then can also move itself into an area where it's going to have minimum amount of repulsion. Key thing for us, and I guess the good news is that we don't need to forget everything we've learned about atomic theory, that we don't need to forget everything we know about atomic orbitals. The good news for us is that this will only be used when we're making molecules, when we're forming molecular orbitals. Now, if you go on in chemistry, and I hope you do, and you learn more about molecular orbitals, you'll go into much, much more detail than we're going to. It gets pretty heady. For us, you don't need to write this down. For us, the big thing is, as I have new factors coming into it, so electrons repelling, bigger groups trying to bond in, and forming more electron pairs, those kinds of things are going to be able to push the electrons away. I know that from VSEPR, but because I have electrons that are not in a fixed location, they can do whatever they want. So let's start with hybrid orbitals. And the first one we're going to look at is called an sp hybrid. And it's not the most creative of names, but if you look at a system like this, where I've got 2 electrons in the s orbital, rather, and I have empty but available p orbitals, then what's going to happen, or what could happen, is that I'm going to promote one of those electrons. I'm going to move it from that pair, I'm going to move it up into an empty orbital so that I have 2 singles. Now that works for bonding, so I can pair with either, or pair with both rather, electrons. However, that's not a hybrid. The hybridization comes when I mix those 2 orbitals, combine them somehow, and I end up with a brand new kind of orbital, which I'm going to, or I'm not going to, has been cleverly called an sp orbital. And that leaves me with a couple of p orbitals that I'm not using at all. Now, if I look at this in pictures based on what we know s orbitals and p orbitals to look like, then what I have is something like this. You'll notice that I start with 2 orbitals, I finish with 2 orbitals. The orbitals have features that are similar to both s orbitals and p orbitals. So it's got that big bulgy part like an s orbital, but 2 lobes like a p orbital. Now, of course, the larger area, which is where I'm more likely to find the electron, that is where the bond, the overlap of orbitals, will be occurring. You'll also notice that when they combine onto one nucleus, because in that middle picture there, they're separate, but they actually do exist on one atom. Then I have these 2 lobes. You don't really see that back lobe, that smaller back lobe. I have 2 lobes, 2 separate orbitals. Now they are at 180 degrees apart from each other. I've got a linear arrangement. I can combine more orbitals. So if I look at this system where I've got 2 electrons in the s, 1 in the p, 3 electrons in total, 3 valence electrons, so I could potentially form 3 bonds. I'm going to do a similar kind of thing. I'm going to promote, and then I'm going to hybridize. So I'm now involving 3 orbitals. So if I start with 3 orbitals, I expect to finish with 3 orbitals. And indeed I do. And in this case, what I have is 3 orbitals that have been cleverly called sp². Why sp²? Because I'm taking 1 from the s orbital and 2 from the p orbitals, and that gives me 3 orbitals. So I'm using those superscript numbers a little bit differently than when I'm doing electron configuration, even though I'm using similar notation. So please keep it straight. And I still have that 1 p orbital that I'm not using. If I now look at this, where I combine 3 orbitals and I finish with 3 orbitals, they still have that same somewhere in between s and somewhere in between p character. I now have 3 orbitals that can orient themselves as far away from each other as possible, giving me a trigonal planar. So it's consistent with VSEPR theory. If I keep that going, now I can have sp3. So all 3 p orbitals and the 1 in the s. And that's so I have now a total of 4 orbitals. And similar as last time, I can promote, and this would be something like carbon. Remember the 4 valence electrons? Promote an electron up into the p orbital. So now I have 4 single electrons. Hybridize, combine all 3, and I end up with 4 sp3 hybrid orbitals. And if you think about carbon for a moment, we know that carbon has 4 bonds. Carbon behaves like it has 4 single electrons around it. Always has 4 bonds, no more, no less, no exceptions. They won't always be 4 single bonds, but that becomes something we'll talk about in class. sp3 orbitals, as I mentioned, and we don't have any p orbitals left. If I did that, so I'd start with 4 orbitals, I finish with 4 orbitals. My orbitals initially, as you can see, are the p orbitals, up, down, left, right, in, out, all oriented 90 degrees to each other, plus that s orbital that's kind of kicking around over all of that. However, once I've hybridized, now I can have these orbitals that orient themselves as far away from each other as possible, and I have the tetrahedral shape. Now, not everything that does this will always have 4 single electrons. It won't even necessarily have a promotion to an orbital. So if I think about lone pairs, then this one with 6 valence electrons, 2 in the s, 4 in the p, 6 valence electrons is probably going to be an oxygen or something like that, but in this case we'll use oxygen. I don't need to promote anymore, but I will hybridize. And if I hybridize these 4 orbitals and end up with my sp3 hybrid orbitals again, then what I have is 2 lone pairs and 2 single electrons. And if you think about the structure of water, the Lewis diagram of water, it's going to look something like this, where I've got 2 lone pairs and I've got spots for 2 single bonds. I can keep this going. Now I can include things that would be involving more than an octet of electrons around that central atom. So for example, if I look at this system, now normally this would be, say, phosphorus. Phosphorus, I would say 5 valence electrons. I wouldn't normally think about those d orbitals because they are not being used on a sulfur atom. But I said sulfur, phosphorus atom. Phosphorus, I don't normally use the d electrons, or there are no d electrons, but I don't normally use the d orbitals. But if I want to now hybridize and, again, promote an electron into one of those d orbitals, and then hybridize all 5 of them, Now I can have 5 new orbitals of a new type, and I could call that sp3 because I'm using S and 3 Ps, and a D, so sp3d hybrid orbitals, and that's exactly what I call it. I still have those d orbitals that I'm not using, and that allows me to have the space for a trigonal bipyramidal, okay, that we see. Keep the thinking going. So now I know on my VSEPR shapes, I go up as high as octahedral, where my central atom has 6 things around it. So if I look at this system, again, I'm probably going to call this sulfur, because I called the last one sulfur too, but I'm going to call this one sulfur because it is 6 valence electrons, much like oxygen, but the difference now is, unlike oxygen, sulfur has, in the 3rd energy level, has possible d orbitals. So if I start to use some of those, promote 2 electrons up into d orbitals, hybridize 6 orbitals now, I end up with 6 orbitals that we call sp3d2. That is going to give me an octahedral shape. Now, a couple of final thoughts. Actually, just one major one is that for us, all single bonds will have hybrid orbitals. So in other words, we don't have to worry about when do I use hybrid orbitals, when do I not use hybrid orbitals. Anytime you're forming single bonds in a molecule, we're going to think of it as hybrid orbitals. That gives us the opportunity to put our bonding pairs and our lone pairs as far away from each other as possible. After that, we're going to sit down, we're going to spend some time trying to figure out, connect the 3 things. Right? We have Lewis diagrams, we have hybrid orbitals, and we have VSEPR shapes, or the geometry. And we need to be able to include all of those 3 things together. Anyhow, we'll work on this in class. Talk to you then.